So we're going to end this section with just a couple more short examples with interpreting some higher order derivatives. I should have probably went to this summary at the end of the last video here. We went through a problem that involved position and velocity and acceleration. And so this is from your book in this section. I'm actually going to add to this a little bit, and actually this is something you'll come back to many times throughout the semester. So if acceleration is just due to gravity, like negative 9.8 meters per second squared is acceleration due to gravity. In that situation, I think last time we were using feet per second, so negative 32 feet per second squared. Then the velocity is the negative whatever that gravity is times t. And in general, actually, we end up having an arbitrary constant here. So let's see here. You can add in, so I'm going to just add in right here, plus whatever your initial velocity is. So if there is some sort of initial velocity, then that is this v sub 0. And it's not crucial that you have these three formulas memorized, but it's just kind of useful to make this observation. We're going to come back to this many times throughout the course. And then the position function ends up being negative 1/2 of that gravity times t squared. And then if there was some sort of an initial velocity, it's going to be plus that initial velocity times t, and then plus s sub 0, where s sub 0 is going to represent the initial height, or the initial, I'll just generically refer to it as the initial position. So these are kind of your general three forms for acceleration just due to gravity, like an object thrown into the air and coming back down. So again, not anything that's, going to require you to, at this point, go out and do any memorization, I would say, of this, but it is something that we will kind of come back to here. So I just wanted to extend that a little bit here. All right, so extend my box. Now let's look at no computations in this next example, but just making an interpretation. So suppose that P of t gives the population of a town t years after the year 2000. So first let's interpret P of 19 equals 5,000. So this is just the original function. So this is just saying then that in the year t years after 2000, so that would be in the year 2019, so at that time, the output of this function, well, this is all about population, so the population is, or was, 5,000 people. Okay, so just the basic original function. Input, output with labels. All right, the next one we have the first derivative, the rate of change. So again, it's important to say at the point of interest, so at, in this case, t equals 19, practically speaking, in the year 2000. Now we're talking about how fast the population is changing. The derivative is the rate of change of that original function. So we would say something like the population is, and it's positive, that derivative is, so we would say it's growing. So the population is growing, and the value of that derivative is 500, and the label is important. The label of a derivative is always that output per input label of the original function. So here that would look like 500 people per year. So in 2019, the population was 5,000 people, but it was growing by 500 people per year at that instant. Now, the last one is the second derivative. So the second derivative is going to describe, again, at that point of interest of the problem, so here in the year 2019. But the second derivative is describing the rate of change of the first derivative. So if the first derivative, if we kind of generically think of that as the growth rate function, The second derivative is describing if the growth rate function is either increasing or decreasing. Is the growth, in this case, it's negative, so the growth rate, the growth is actually decreasing. So we might say something like, in the year 2019, the growth rate of the population, or the rate of change of the population, I kind of like the growth rate of the population, is actually slowing because of the negative, or decreasing, but it's actually slowing down by 50, and again, the label's important. It would be the output label of the quote original function, which in this case the original it's describing is the first derivative. So people per year per that input label, which is per year. Okay, or of course we could say this as people per year squared. So the population is still growing, but the rate at which it's growing, its growth rate is slowing. And so right now, as I sit here and record this video, the most common place you're seeing this in at this time is talking about the coronavirus, and all they want to do right now is to get that growth rate to slow. So there's been this very rapid growth of the number of cases and the number of deaths, and they're trying to slow the growth. So that's all. Every time I hear that, I just hear second derivatives. All right, last example. We have a little comic here, and it says, I'm proud to report, Garfield said, I only gained 1 pound. And so the punchline says, with Garfield, the goal of the diet isn't losing weight, it's slowing down the gain. So before we get into what I'm going to ask us to fill in here, let's first just kind of think about what a sample graph of this function might look like. So maybe we have maybe a graph with respect to time. So we're going to say maybe this is his time. I don't know. Let's give it an actual time, a unit of time. Let's say this is in terms of weeks. And this is the actual weight, let's say, in pounds. And he's still gaining weight, but his goal is slowing down the gain. So while he is still gaining weight, he is slowing his gain. So that's what we're looking at here. So he's slowing down his gain. So that's kind of the key feature on this graph. It's the, again, slowing the gain is what we're seeing, especially kind of towards the end of that graph here, is really slowing it down a lot. So if you think about these functions, the original function, the first and the second derivative, so this is the original function here. So let's just kind of note, I guess I'll say, off to the side before we jump in and try to interpret anything, that the original function is simply his weight at any point in time. So this is just, you know, his weight, and we would just label that like in pounds at any particular time. The first derivative then is the rate of change of his weight. And in this situation, it's a weight gain situation. He's still gaining weight. That's described in the problem. So the first derivative is really describing his weight, his rate of change of his weight, but we know it to be a weight gain. And we would label that in pounds per week. Then the second derivative is describing, honestly, this is a bit like, I should have varied it up a little bit, but it's a bit like number 2, because he's really talking about wanting to slow his gain. But the second derivative is the rate of change of his weight gain. So it's how fast his weight gain is changing in like pounds per week or pounds per week squared. Okay, so that's just kind of familiarizing ourselves with the functions before we kind of jump in and then look at the filling in of the appropriate inequalities. So for Garfield, it says the goal of a diet is not, so notice the negative. So for goal of the diet is not losing weight. So this is what the joke said. His goal is not losing weight. So I have to fill in the right inequality that represents weight loss. So think about, if you were graphing a function that was representing, weight gain and then weight loss. So if I was to think about what losing weight might look like here, what would losing weight look like? Well, his weight function would be decreasing, right? So in that situation, it would be, again, this is supposed to kind of represent the same type of situation here. This is like a W of t function. But if you were to think about then the slope of the tangent line or the rate of change here at any point, it would be negative. So losing weight is going to mean that the derivative, w prime, would be less than 0. So if we're losing weight, the derivative, the rate of change of the weight, would be negative, would be less than 0. So his goal is not losing weight. It's not that w prime, it's less than 0. It is, and so what is his goal? His goal is slowing the gain. So he is trying to slowing the weight gain. And again, that's kind of what I have in that opening graph up above, kind of showing, so again, pounds, and this is in our weeks here. But in that original graph, we're seeing that he is slowing the gain. And so let's think about what happens here to your tangent lines if you were to draw them in as weight gain slows. So think about the slope of your tangent lines and what is happening as my weight gain is slowing. The slopes of the tangent lines, the w primes, if you will, they are actually decreasing. So the rate of change of the derivative, the rate of change of the slopes of those tangent lines, if you look at it that way, they are actually decreasing. They are getting smaller. So this would be that our second derivative is less than 0. If we were speeding up the gain, just as a comparison, it would look something like this, where the slopes of your tangent lines, the derivative would actually be increasing. So the slopes would be getting more steep if you were actually speeding up. If you were speeding up your rate of change, those slopes would be getting more steep. And in that case, the w double prime, the second derivative, would actually be greater than 0. So we kind of took all the fun out of that joke, but just one more little interpret problem there. So that wraps up section 2.4. When we come back next time in 2.5, we're going to be looking at derivatives, as you can see right here, of our trig functions.